Hello students, today we are going to study something about semiconductors and semiconductor devices. The chapter's name is electronic devices. So I hope you are well familiar with the current electricity topics and have a little bit knowledge of chemistry. That is because we would need something of that sort of knowledge about electronic configuration. However, if you don't know about it, don't worry. I will try to explain this but still in brief. So first, let's start with the concept. What is semiconductor? You might have heard that some materials like silicon, germanium, they are used in making electronic devices like computers, their chips, the circuit boards, etc. You might have also heard the concepts of diode, transistors, photovoltaic cell. So all these things use some kind of semiconductor, and their uses are quite different from one to another, but some things are quite similar. For example, all semiconductors means semiconductors in all these devices are used only because they have the ability to conduct electricity very selectively. So first, let's understand what is semiconductor. So there are types of materials which can conduct electricity very easily, like metals, solutions containing ions like NaCl solutions. So you might have heard that when any electrolyte or any aqueous solution with salt breaks the lattice structure of that compound into ions, suppose NaCl, they break it into Na plus and Cl minus, and because of free ions they are able to conduct electricity because ions can move freely. So the concept why electricity can be conducted by one type of material and cannot by another is because of availability of carriers. So what are carriers? In metals, carriers are electrons. So you can say that if there are electrons, you can expect them to conduct electricity, but every matter has electrons because every matter has atom and every atom has electrons. So why don't all atoms can conduct electricity? Or in other words, I would say, what is the limitation for some part of some types of materials that their electrons are not able to conduct electricity? So the answer is their electronic configuration. For example, take the electronic configuration of a very simple electronic configuration. Suppose Na, that is sodium metal. Can you recall the electronic configuration of sodium metal? We know that sodium accepts one electron. Sodium gives off one electron to become a positively charged ion. It has a single positive charge. To go deep into its electronic configuration, let's see what it has. So How many electrons does it have? A total of 11. The atomic number of sodium is 11. And if you break it, means if you try to analyze it in terms of electronic configuration, it has 2s1, sorry, 1s2. 1s2 means the first s orbital containing 2 electrons, then second 2s2, then 2p6, and then we have a 3s orbital and a 3p orbital. But if you count the electrons 2, then 2, there are 4, and then 6, that is 6 plus 4, 10. We have only one electron left, that is in our third s orbital. So our p orbital, the third p orbital, doesn't have anything, no electrons at all. However, it can contain 6, but since we don't have any electrons, there would not be any p orbital. So what happens? We call these parts as completely filled orbitals, because whatever they can accommodate, they have already. So what about this part 3s1? You know, in chemistry you have heard that because of this third incomplete orbital, sodium is a very easy donor, means it is highly electropositive, it is eager to donate its electron, and that's why it becomes positively charged Na plus ion, and it reacts with electronegative elements like chlorine, fluorine, iodine, etc. It also reacts with sodium, means being so reactive, it can react with many other compounds, many other elements. So but here in the concept of physics, we are talking about how it can help in conduction of electrons. So obviously it has a structure where electrons can move freely. So let's say this is our sodium nucleus. I'm just trying to make it a little bit clumsy. So this is the nucleus and some electrons orbiting around it. So we can say this is the innermost, 2s2, then 2p6. So we have 2 electrons in innermost part, 2 in the next innermost, and 6 in the second outermost, and we have 1 electron quite easily available for sharing. So if you have a similar structure, suppose another nucleus of this kind and same internal structure, and then an outer electron here, that means when several Na atoms are clubbed together, what happens, this being the energy level of this electron quite high, it can move from one to another because not much energy is needed to make it escape from here. And the same, if there will be surplus here, it can escape to another, and from here it can escape to another. So you can see that the electron here is quite mobile, and that's why if an electric field is created here, what will happen? The electrons will tend to move towards against the direction of electric field. That you know that electrons are negative charged particles, they would move against electric field. So this is how we get conduction of electrons in metals. What about non-metals or non-conductor? We also call them insulators. So what happens? Suppose this is the nucleus and this, we have this outer one valence band, and then this is the band here, and might be there are other bands as well, but what the point is that all atoms are quite satisfied with their electronic configuration, and electrons are well stabilized. No energy transfer, no means very small fluctuation of energy transfer or electric field would not affect the electronic configuration of these things. The electron will not jump out. If there are energy is provided to this electron, they will simply move to a slightly higher energy state, and they will come back giving off some radiation and nothing else. They will not move out, they will not conduct electricity. So something must be there, like there's one way, like metals and with the free electrons there are non-conductors, means suppose how would you say, diamond, wood, plastic, or a carbon atom simply. They would not give off electrons so easily, so they have stable electronic configuration, and conduction of electricity is not easy for this. It cannot be said impossible, because every particle or every matter can conduct electricity at very, very high potential difference. Means if you provide extremely high voltage against anything, even air can conduct electricity at very high voltage, but we are not going into that matter right now. So if we consider the conductivity, I'm using this symbol small sigma, conductivity of copper, just to compare how the conductivity or the conduction of electrons varies from one material to another. So copper to, we are comparing copper and fused quartz. You might have heard about this matter. Fused quartz is supposed to be very, very good insulator. It doesn't allow to pass electricity even at very high electric field, provided this is beyond the range of extremely high where everything is conductive. So you know, if we compare this thing, we know that the conductivity of fused quartz is quite less as compared to copper, and the comparison is such that the conductivity of this thing, copper, is equal to 10 to the power 23 times or 24 times around. Yeah, it is 10 to the power 24 times of quartz, fused quartz. Now compare something in between, like not obviously so good insulator, but not very easily conductive. There are materials like silicon, germanium. Their electronic configuration is such that they can jump off the electrons from quite non-conducting level to some kind of conduction level. So you can say that if we are comparing the conductivity of these materials, the conductivity of silicon is 10 to the power 11 times smaller than conductivity of copper, and again 10 to the power 13 times greater than that of fused quartz. So this is these kind of materials, silicon and germanium, they are called semiconductors. They're also called semi-metals. That's means you have heard about this in chemistry classes, and you will come to know more about this even in this class. So what's so different between these type of metals? So we just came to know about the valence electrons, conduction electrons that is available to conduct electricity in sodium types of metal. There are other types of metal in which there is no one fixed electron for sharing, but what happens that there are electrons available in the form of electron cloud, and they are quite mobile. For example, metals like zinc, what happens in their electronic configuration, the energy level of electrons are so close to each other that one slight change in electric fields, even a small electric field can disturb the electrons, and they can, one stable electron can be sent off to a higher energy state so that they can contribute to the conduction from one atom to another. Means they, if electron is jumping from one atom to another, you can simply say that electrons are transferring, so electric current is taking place here. Means electric current is flowing, electricity is flowing through that matter. So in zinc type metals, unlike sodium type metals, they don't have one definite electron for sharing, but they have several electrons in overlapping zones. So you can say, if we divide electrons into two types, one say valence bond, one being in valence band and one being in conduction band. Valence band electrons are those which take part in reactions, maintain the electronic configuration, but doesn't take part in conduction of electricity. While conduction band, electrons in the conduction band are quite available for sharing, moving from one atom to another. They are freely available from jumping from one to another. Before we go to how this happens in semiconductors, let's go to a concept of mean free path. So what is mean free path? Electrons travel from, so let's say this is a wire and there are atoms in this wire. I would definitely say that in a wire there would be not only 2 lines of atoms, there would be 1,000 and even much more than that. But I'm just trying to show that how electrons would travel. So if there is an electric field in this direction and an electron starts from here, so do you think that they will flow uninterrupted? No, there are other atoms, right? So it will collide, it will hit one atom, then it might get attracted to another atom, and it might lose its energy and starts residing there and say I'm not moving at all. So what is happening here? One electron moving from here, moved here, and before it collides to some other, it has moved a path d, distance d, and after collision it moved there, another d, d1, d2, then d3, then d4, and so on. Means it will not flawlessly or without any obstacle it will flow like that. It will not happen. It will have to overcome all the obstacles, and the same will happen to all the electrons. So there is a concept of mean free path, that every electron in its journey has to cover some path without any disturbance, and the mean of that path is called mean free path. So let's consider, I have one question from one of our textbooks which tells us the mean path of a conduction electron in copper is 4.10 to the power minus 8 meter. Find the electric field which is required to give this electron an energy of 1 electron volt. You know the energy of 1 electron volt is quite easily distinguishable from joule. Joule is a SI unit, and if you relate these two, 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. So here the question is, what is the electric field that is needed to give this electron an energy of 1 electron volt? So what's happening here? The mean free path means electron has started from one place and gets collides at another, and this mean free path is suppose d, and the value of d is given as 4 times 10 to the power minus 8 meter, and it is asked that which electric field, what amount of electric field is needed to give this electron energy of 1 electron volt. So the first thing is, we would consider the force given by that electric field. Let's say that electric field is E. Means the magnitude of this is E, not E vector. So what would be the force on this electron? Would that be E times small e? Well, this small e is the charge of electron. Okay, and we know that energy given to one particle is equal to the force times distance. Means obviously the work done is equal to the energy acquired by that particle. So energy is equal to work done on that, and we know that work done is equal to force times displacement. We know that displacement is d here. I think I'm overcrowding this page. Let's try to do it here. So let's say here we have our question here, and what we were finding here, we were finding the electric field E, which will give the final energy as 1 electron volt, that is 1.6 into 1.6 into 10 to the power minus 19 joule. We know that the force would on this electron equals to E times E, and the distance means the energy acquired in the mean free path. Mean free path is d, would be E, capital E times small e times d. This would be the energy. Why? This is the force, this is the displacement. Energy equals to work, and work equals to force times displacement. So what would be that E? We know that E times D. D is 4 times 10 to the power minus 8 meter equals to 1.6 into 10 to the power minus 19 joule. So why don't we simply say 1 electron volt, right? 1 electron volt. Why are we using it in joule? No, we'll start with this. So 1 electron volt we know is equal to 1 volt times charge on 1 electron, that is E. That is the definition of one electron, right? That the energy acquired by 1 electron when it moves through the potential difference of 1 volt into influenced by the electric field itself, obviously. So if we solve this equation, we will get E equals to E times 4 times 4 10 to the power minus 8 meter equals to 1 volt. Small e getting cancelled from both sides, that gives us 1 volt. So the electric field E equals to 1 volt divided by 4 times 10 to the power minus 8 meter. What is the electric field here? Volt divided by meter. Volt per meter is the unit, and the electric field would be, what would be 0.25 into 10 to the power 8, right? And that comes out to be 2.5 into 10 to the power 7 volt per meter. So this is a very basic kind of numerical, but this gives you an idea of what mean free path, how mean free path could affect the required electric field, and how an electric field is associated with the change in energy structure, or say change in the energy acquired by 1 electron. So you see that this high amount of electric field, 2.5 into 10 to the power 7 volt per meter, has given 1 electron volt of energy to an electron in copper, because we have just said that this is inside copper, and mean free path inside copper is around 4 times 10 to the power minus 8. So this is just to feed you one numerical from this chapter. We can move ahead with the theory part, because this chapter is quite theoretical. Those students who are quite interested in numericals often get bored with such chapters. So now talk about valence and conduction band. In terms of these two things, band. So what is band? Band is obviously group, right? When you talk about music band, you say that there are certain people who are clubbing together to create music or play music, so that is music band. Here we are talking about valence band and conduction band. So there must be one group. You can say that at times there's only 1 electron in the band, means that could be a very lonely electron, just like in the case of sodium. So in case of metals, there are 2 different types of band. One, we can simply say one has sodium type metal and one zinc type metal. In sodium type metal, the conduction band and valence band, let's say this is conduction band and this is valence band. The conduction band is completely filled. You see that the inner electronic orbitals are already filled in sodium, while the outer one, that was 3s2, you remember, if you look back in the video, in the lesson itself, only the outer is partially filled. So partially filled electrons can move out, obviously, because they are not paired and they have the ability to move around more than the completely filled orbitals, because they are quite stable in terms of energy. Now talk about zinc type metals. If you talk about zinc type metals, most of the metals that are used in wires and electronic usages, those are zinc type metals, because they have this first, you know that sodium type metals are not so good in uses of electricity, like, because they are soft, they are very reactive. So you see that if you have used a wire in your house, and on a moist day all your wires burn up because it has reacted with water. So sodium cannot be used in those cases. So we use iron, copper, aluminium, those kind of metals. Zinc is also a good metal, but obviously we don't use much in electronic uses. But still, these have similar kind of properties in terms of conduction of electrons. So what happens with these type of electrons? You see, the inner part, the conduction band is almost completely filled. The valence band is also almost completely filled. But what happens whenever there is even a little bit of energy difference because of electric field or something? Some electrons jump from conduction band to valence band, and this is very easy for all these metals. And because of these small jumps, there are plenty of electrons available for conduction of electrons. Now consider non-metals. We have this valence band. So did I say? I'm so sorry, please look at this again. I have written valence band, conduction band below. It should be valence band, not conduction band. Well, conduction band has higher energy than valence band, and they are responsible for conduction of electrons. So valence band is obviously below and conduction band is above in energy level. So what happens in non-metals? The energy difference is quite high, and not very small changes in energy, very considerable amount of electric field will not make electrons jump from here to here. They will have to eventually come down. So no electricity will take place unless the electric field that is applied is ultra high. Now consider the case of a semi-metal or say semiconductor. In semiconductors, the valence band and the conduction band, they are distinct. They are not overlapping like in case of metals. They are not half filled like in sodium type metals. You can say that the valence band is filled and stable, conduction band is completely empty, but the energy difference is very low. Means quite high as compared to metals, but quite low as compared to non-metals or insulators. So these are semiconductors. An example of semiconductors are silicon and germanium. Now what makes a semiconductor more conductive? Like, how can we increase the conductivity? Obviously, a semiconductor in its general properties is not so useful in making electronic devices, that because they are not good in conduction. Obviously, we need some of their properties. For that, we one way of doing that is changing the temperature. If you increase the temperature of silicon or germanium semiconductor, their conduction will increase. Unlike metals, we know that for metals the conductivity decreases when temperature increases, but semiconductor, when temperature is increased, conductivity also increases. So can you say that you make an electronic device and then to make it work you heat it and then you cool it down so that the effect would be working? I don't think so. That would not be a good idea. So for that, there is another way of changing its conductivity or resistivity. Obviously, you know that resistivity is nothing but the reciprocal of conductivity, be it metal, non-metal, semi-metal, semiconductor, or any kind of thing. So this is how this is. We give the symbol rho for resistivity and sigma, small sigma, for conductivity. So to make a semiconductor a better conductor, we dope it. Doping means we deliberately, intentionally give impurities into that. So one example we are taking is of silicon. We know that silicon has 4 electrons that are available for bonding, and the structure is quite stable in somehow. What happens? This silicon shares 1 electron with this neighbor, 1 electron with this neighbor, 1 electron with this neighbor, 1 electron, and here means one silicon is attached to 4 silicons in their neighborhood, and they share the electrons such that each has its octet completely. That means they have a full outermost shell. So that's why the electrons are not so easily available for conduction. So what we can do, we can disturb this quite stable structures so that the electrons become available. So one thing is we just put an electron here, right? But can we put electrons into some metals? No, we cannot. We don't have electrons available for making like impurities, or we cannot control electrons like that. So what we do, we put impurities which has different electronic configuration but not exactly away from this. So it has 4 electrons out in their outermost shell. So we will look for those who have 3 or 5. Why? Let me tell you. So let me remove this silicon and put a phosphorus here. You know, phosphorus has 5, so 5 electrons in its outer shell. So 4 will work in the same way as earlier, means like silicon, but 1 electron is still available, and this is a negative charge that is free for electronic conduction. Now if an electronic an electric field is applied, what will happen? This electron which is moving here or there, it will start jumping from one atom to another away, opposite to the direction of electric field, and it will go like that. But say if we are not using phosphorus but we are using another thing like aluminium. What's different in aluminium? Aluminium has 3 electrons in an outermost shell for bonding. So what will aluminium do? Aluminium, 3 of it will bond with the neighbors, but 1 will not be bonding, and there will be 1 vacancy. Let's say this is a vacancy. So vacancy doesn't travel, right? But electrons can. So electrons from this bond would travel to here, and vacancy would be cleared here, and from here another electron will jump to here, and so the vacancy can also travel. However, vacancy is not traveling, it is the electron that is traveling. So one type, in silicon we saw 2 types of doping. One is phosphorus type doping and one is aluminium type doping. Phosphorus has 4 extra electrons, aluminium had 3 extra electrons, means outermost electrons. Phosphorus gave rise to 1 extra electron, and aluminium gave rise to 1 vacancy. This kind of doping, phosphorus type doping, is called donor doping. I think this is also named by a different name. Yeah, that is the positive doping and negative doping. So since this is giving an electron extra, so this is a negative type doping, or am I wrong? Yeah. I might have something handy for me to look at that. Yeah. Yes, since this is creating an extra electron, this is the donor doping. Because this is a donor of electron, we have an extra negative charge. This is called negative type, N-type doping. And this will, aluminium, this will create an acceptor type doping, because it is accepting more electrons. So this will create a vacancy, and this is called P-type doping. Obviously, now to avoid confusion, what is N-type doping and what is N-type and what is P-type? N-type means negative type. That means the conducting thing that is introduced here is an electron, that is a negative charge. That's why we have N-type doping. And the conducting thing here is a vacancy. Vacancy means an absence of electron that will make it positively charged. So this is a positive type doping. We cannot move further with this class because we have constraint of time, but in further classes we will make sure that other parts are also covered. And for better understanding of these concepts, you can always refer to Toppr videos, and please let me know in your comments that if you have found any help or not. And if you don't have found any help, you can always go to toppr.com and find your relevant videos there. Okay, thank you very much for staying with me. Have a great time and keep learning. All the best for your exams.